Could you repeat that one more time?
Yes. So,
Yeah. Can you go back to the one that we were talking about?
Yes. So we're going to start with 5.1, the introduction and services. But before we get into that, let's talk about some terminology. Specifically, hosts and routers are nodes. What is a host, by the way? Give me an example of a host.
A host is a type of node that goes along the path.
Give me an example of a host.
Host. Hold on. Like a host is like a IP address?
No. A host would be a computer, a PC, a server. It could be a phone.
It could be a printer.
It can be a printer. Very good. Okay.
Or etc.
So just keep in mind that both hosts and routers, because a router is not a host, well, these are called nodes. And that communication channels that connect adjacent nodes along the communication path are links. All right?
Right.
And links may be wired, they may be wireless, and we may refer them as LAN links. Okay?
Right.
Layer 2 packet is a frame, which are used to encapsulate the layer 3 datagram. Data link layer has a responsibility of transferring data from one node to an adjacent node over a link. Okay?
So data link has provided data from one node to so that the communication link that connects adjacent node to another a communication link that connects adjacent node to the communication path.
Right. So here we have, do you see right here? I've got a PC. And then a router. And what's happening is the PC is a node, the router is a node, and there's a connection between the PC and the router, and that is our link, or one of the links. Okay?
Yeah.
All right. And again, remember that a frame is the packet in the link layer, okay?
Frame packet in the link layer.
Yep. All right. So a datagram transferred by different link protocols over different links, such as Ethernet on the first link, frame relay on an intermediate link, and then 802.11 on the last link. What is 802.11?
802.11 on the last link.
Yes, but what is it? Do you know what kind of protocol that is?
It's like an RFC. Hold on. RFC 768 protocol.
Yes, but what? Give me a general idea of what 802.11 is, because there's 11A, there's 11B, there's 11G. But what is 802.11? There's one word I'm looking for.
.11.
.11 is wireless, Sam.
Wireless?
Yes. All of your wireless protocols are under the 802.11.
Okay.
So what they're saying here is that depending upon the link, right, we're going to use different types of data link protocols, okay?
Right.
For instance, this link right here between this PC and this router, that's probably an Ethernet link, okay?
Right.
Whereas the link between this laptop and this wireless access point is an 802.11 link. Now, you'll notice that we've got a link between here and here, okay? These are two different ASs, autonomous systems. And this link here might be, this data link protocol that runs here might be frame relay. Frame relay is an older WAN link, okay? You don't see it much today, okay?
Right.
Today, you see a lot more of MPLS, okay? All right, so there are going to be different protocols over different kinds of links. Each link protocol provides different types of services, okay? They may or may not provide RDT over a link, okay?
Right.
So let's take a look at this analogy. You're going to be taking a trip, all right, from Princeton to Lausanne, okay? And for part of the trip, okay, the local part of the trip, you're going to use a limo, and you're going to travel from Princeton to JFK. Then, for kind of the WAN link, if you will, you're going to take a plane, because this is long distance, from JFK to Geneva. And then you're going to take a train from Geneva to Lausanne. Okay?
So if you can take like a car and drive it to Florida.
Well, let me ask a question. Different links do different things, okay? Would you drive from JFK to Geneva?
No, you would take the plane.
Right. You can take a limo from Princeton to JFK, but you would never drive from JFK to Geneva. You're going to use a different type of link. And in this case, you're going to use a plane. But from a networking terminology, okay, we're going to use some kind of WAN, all right, WAN protocol. Okay?
Protocol.
So in this analogy, the torus is equal to the datagram, okay? Because the torus is what we're trying to transmit through this connection from Princeton to Lausanne. Okay, we're trying to transport the tourist. Okay. The transport segment is one of the communication links. The transport mode is that particular link's link layer protocol. And then finally, the travel agent is the routing algorithm. And different data link layer protocols have different algorithms, which is what we'll be getting into very shortly. Okay, so framing and link access. When we talk about framing, we're basically talking about taking data that is coming down from layer number 3, which is, you tell me what layer number 3 is.
It's a link layer protocol.
No. What layer number 2 is the data link layer. What is layer number 3?
That is routers.
Routers, but what layer do we call that? What's the name of that layer typically?
That's layer 2.
No. Layer 2 is data link layer. What's layer number 3?
Maybe it's
Sam, let's remember what all the layers are. Okay, how many layers are in the OSI model?
7 layers.
Okay, so starting from the bottom, what's the first layer?
It's the it's segments.
What is it?
Segments.
I can't hear you.
Segments.
No.
It's we have the transport layer.
Nope. We're at the bottom. At the bottom, Sam. Here you go.
Yep. Okay. Give me 1 second. It is the physical layer.
Right. What's layer number 2?
Data link,
Layer number 3.
network, and
you've got transport, session, presentation, and application.
application.
Okay. What are these over here on the right-hand side?
They are bits, frame, packet, PPDU, FPDU, PPDU, and APDU.
Yes, but can you tell me a little bit more about what they're trying to tell us here?
The physical layer operates in bits.
Correct. Physical layer operates in bits. The data
link
layer uses what?
Frames. And the network layer uses packets.
And what's TPDU?
I don't know what that one is.
Okay, I've never seen it abbreviated that way, but they're saying that it's the Transport Protocol Data Unit.
Transport data. I don't think he ever.
Yeah, no. Okay, but I just wanted you to understand. The next one up, the Session Protocol Data Unit, then the Presentation Protocol Data Unit, and finally the Application Protocol Data Unit.
Okay, could you?
Okay. Let's see if we've got a better diagram here. Yeah, this is a little better. Can you read this? Tell you what, let me go back here. There are definitely better pictures than this. These are pretty lame. Okay, here we go. So as you can see, this thing breaks it down into upper layer protocols and then lower layer protocols. You've got your physical, data link, network, transport, session, presentation, and application, and a brief description for each one.
It's a bit stream physical media method of representing bits. And the error detection, and then a data link layer is error detection, flow control on physical link. And the network layer is network addressing, routing, or switching. And transport layer is end-to-end error control. And session layer, authentication permissions, session restoration. Presentation layer, coding into ones and zero, encryption, compression. Application layer is message format, human machine interfaces.
Okay, very good. So let's look at another diagram. So these are some of the different protocols. So in the physical layer, we've got things like Ethernet and token ring, and devices such as hubs and repeaters. And then in the data link layer, we've got Ethernet and ATM, and devices such as switches and bridges. Then we're into the network layer, which runs IP, ICMP, and IPX. And IPX is an older protocol. And the device that this typically runs on is a router. And then above that, we have TCP, UDP, and SPX. Okay, and then after that, we get into our application layers, the upper layers. Okay.
Session. Comes in the upper layer like switch and bridges. Could you write these down?
Well, it's all right here. Okay. What I can do is I can capture this, copy the image, and let me open up Microsoft Word here. Okay. I'll send this over to you later on.
Okay.
Good. So we've got that. Okay.
Okay.
So again, when we talk about encapsulation of a datagram from layer number 3, we're basically putting that into what is called a frame. A frame is the PDU, or the protocol data unit, used in the data link layer.
Right.
And when we create this frame, we add a header information and then sometimes trailer information. Okay. The other thing that we have to work on is what's called channel access if shared. Okay. Now, do we have, when we talked about, let me pull this up. When we talked about switches versus hubs, what's one of the problems with a hub? A hub is what kind of device? What layer does a hub work in?
Physical layer.
Physical layer. And a hub works very much like a bus, okay? In that the hub repeats everything that it hears. And if two or more devices, nodes, okay, or hosts, attempt to communicate at the same time, then we have a what?
Then we have bus. What is it called?
Collisions. Right?
Right. Collision. Could you write?
Let's see. Alrighty.
Collisions occur when two or more hosts attempt to transmit at the same time.
Correct. So, if two devices can collide with one another, which is not a good thing, we have to find out, or we have to have a way of giving access to people, okay, so that we take turns, okay, because only one device is allowed to communicate at a time. All right?
Right.
Now, in a classroom, if, let's say, a student wants to ask a question or make a comment, what does the protocol in the classroom say that the student must do first in order to avoid colliding with another student?
Just wait a turn.
Well, wait their turn, but also to raise their hand.
Raise their hand.
Okay, so what happens is by raising their hand, they indicate that they have something to transmit. And it's the instructor, okay, who then controls the conversation and basically will point to the student and say, go ahead with your question. This way, we avoid 2 or more students attempting to communicate at the same time, creating a collision, all right? So in networks, the same is true. Something has to be controlling access. Now, do we have the same problems of collisions in switches?
No.
No, we do not, because every port on a switch is its own collision domain.
Could you write this down?
Okay?
Okay, so how about routers?
Routers are like all a router is a node on that particular network segment. Okay, but routers they do not allow collisions to go beyond that given port. Okay.
Yeah, for that router, do you have to know that for the exam, or?
Well, you have to know, okay, that anything connected to a hub is a collision domain. Okay?
Right.
Anything that's connected to a switch is it's essentially a collision domain of one device, unless it's a hub.
Could you write that down?
Well, I've written it down here, right here. Okay?
Okay.
I just said it differently. Now, routers can also be used to break up collision domains, but they're not the best device to do that. Okay?
Can you write down something about routers?
Okay. How does that sound?
Could you make the word for the routers that appeal?
I'm sorry, say again.
Could you make the one that you wrote down for the routers that appeal? For routers,
Okay.
could you make the one that you wrote down for routers clearer?
Let me think about it. How do I make that clear? Okay. Routers can be used to break apart collision domains. Okay. Let's do this. Let's work through a problem. Okay.
Okay.
Notice I've got a hub here. Okay.
Right.
How many collision domains are here with this hub?
There is one collision domain.
One collision domain. Now take a look at this this PC here, I. Is there a collision domain there?
Yes. But
Does,
it's on the switch.
right. And is it going to collide with anything else?
No.
So we're not going to have any collisions here, right?
No.
Okay. How about H?
That's another separate collision.
That's a separate collision. So looking at switch number 4, how many collision domains are attached to switch number 4?
3.
Check it.
3. 1, 2, 3, 4.
1, 2, 3, 4, 5. There are 5 collision domains.
5. Where are they getting?
1, right here. 2, 3, 4, 5.
Okay. So we're coming from here. 1, 2, 3, 4, 5.
How many connections are going into switch 4?
5 connections.
There are 5 connections. And what did we say about a switch?
Every port is its own collision domain.
Correct. Okay?
Right.
All right. So, typically, when we design networks, do we want to make collision domains bigger or smaller?
Make it smaller.
We want to make them smaller. We want to keep them as small as possible because collisions are a bad thing. And the smaller the collision domain, in other words, the fewer PCs attached to that collision domain, the fewer collisions you will have. Okay?
Right. So if you just had 2 collisions, there will be a big problem. And if more collisions, there'll be a problem.
No, if the more PCs that you have attached, the more PCs that belong to a collision domain, the higher the probability that a collision is going to happen. I'm sure that you've been in large lecture halls, right?
Yeah.
And many times there's a higher probability of a potential collision with students asking questions simply because there are more students in the classroom, right?
Right.
Well, the same is true in a network where you have many PCs. And remember, it can be not just a PC. It can be any host. The more hosts in a given network segment, the higher the probability for a collision. Now, let me ask a question. Let's say that I increase the number of PCs that are connected directly to this switch. Are we going to have any problem with collisions?
No.
Why not?
Because because it has its own collision domain.
Correct. Very good. It's only when we're using switches that we really run into this when we're using hubs that we run into this problem of a collision domain. Okay?
Right.
Okay, very good. Okay, so we understand that. We're good on that.
Right.
Let's go.
I'm good on the switches. Can we do like a similar problem with switches?
Similar in what way? Do you want me to do another diagram?
A similar, like a diagram of just switches and hubs.
Switches and hubs. Okay. All right. Well, I'll tell you what. Let's pull it up. Let's pull out my old favorite packet tracer program. And we're going to get a couple of PCs in here. Go ahead.
All right, Jim.
All right, good. Now watch what happens.
Wait.
And I just want all right, you ready?
I am.
Okay. So we're going to do a ping from PC3 to PC2, okay?
Okay.
You watch the way this thing how it acts.
All three of these went to three of the PC at the same time. And
I'm sorry.
it goes to the router, and it also goes to three of the other PCs at the same time.
And why does it go to the other PCs at the same time?
Because of collisions, because it's a hub.
No. Not because of collisions, but because it's a hub. A hub does what? What does a hub do when it receives something?
It sends it out. It does a it encapsulates it. When it receives it sends it out. What is it called? It sends it out to.
All right. Well, basically, it broadcasts it out to everyone that it's connected to.
Broadcast it out. But when a switch receives it, it broadcasts it out to the one that it sends it out to, like PC2. But PC1
Right.
and PC2, says if it's not for them, it goes down. But if it's for them, then it encapsulates it. But it sends out a broadcast first.
And why does the router have an X through the packet?
Because the packet sometimes it's not for them, and sometimes the packet will drop.
Well, but again, what happened was the router did not pass that packet on to the other PCs over here.
Right.
Because the router knew that this packet was not going over here. So what you're seeing is the fact that the router killed that packet is showing you how a router can break up a collision domain. Okay?
Right.
And that goes back to our other diagram where we talked about that.
Well, the router breaks it up. Whereas
Right.
switch is a separate domain.
Well, a switch is completely different. A switch has some intelligence, and as you said, after a while, it knows only to send it to PC2 and not to anybody else.
Right.
Why is that? What is the switch looking at to make that determination?
A switch is looking at whether it matches or not, and a switch looks to broadcast to reach the other PC, and the switch is looking at one of them and it sends it out.
Yes, but what is the switch looking at? How does the switch make that decision? It's got to have some kind of information to make that decision. What does it have?
The source MAC address.
It has the source MAC address and the destination MAC address.
Well, the router has the source IP address and the destination IP address. And the router can have... Wait.
All right, very good. So let's redo that, and let's watch what happens, okay?
Okay.
Again, you see the hub. It's going to repeat. It's going to send it out to everybody except from where it came. Except for PC2, everybody's going to drop it. And you see that router 0 stops the packet from going any further because it knows it doesn't. It just doesn't go out there.
Right, because it can't go out further because it breaks it up.
Mm-hmm. All right. Now, let's take this hub out and let's put a switch in, okay?
Okay.
So we're going to take this out. And we're going to put a switch in. And we'll reconnect everything. Okay, and then we're going to one more connection. And we have to give this thing a moment to come up. Okay, you see the orange dots there?
Yeah, so it has to turn on.
Right. So we're about to start the simulation, and if you recall, the first time PC3 sends something out to the switch is going to broadcast it out to everybody because it doesn't know where anything is.
Yeah.
But the second time, it's going to learn where PC2 is, and then you're going to see that it's only going to send to PC2. Right?
Right. The first time it broadcasted out to everybody, but the second time it learns where it is, and then it sends it out just to PC2.
Right. Okay, hold on one second. I got to restart this thing because it's jammed. Let me cycle this. Restart everything. Oh, shoot. I forgot. A moment. Okay, now let's run this test again. Here we go. There it goes to the switch. Now it's going to get broadcast out of here because it doesn't know where PC2 is. Everybody else except PC2 is going to drop it. PC2 sends it back, and it's going to send it directly to PC3 because it knows where PC3 is. So here
Right.
the switch is already showing its intelligence and reducing network traffic.
And then it receives it and then it's decapsulated.
Well, yes. Okay.
Okay. So are we gonna get deep into this right after?
Yes, we're going to get into this much further. Yes. Okay.
Okay.
All right, let's try another something else here. I want to try one more thing to show you. I'm going to do a test from PC1 to PC0, and then we're going from PC3 to PC2. Let's watch what happens. All right.
Right.
Notice that you've got more than two devices that are going to attempt to communicate at the same time, and watch what happens. So at first, what we start seeing is that there's this potential, okay, for a collision, but it doesn't occur because the switch, okay, has broken up all the collision domains. So things occur in a very orderly process. Now, if I can, let me just go back and let me show you again what happens when this is a hub. All right. Now let's do that same simulation and watch all the collisions that occur. Okay, here we go.
Okay.
There we go. We're on our way. Boom. Now it's going to try again. Maybe not. Okay, so what happened was two systems attempted to communicate at the same time, and they collided. Okay.
Then what happens is they couldn't get through because they collided.
Right. So they have to learn to take turns. Now, how in a hub, how do the PCs and an Ethernet network using a hub, how do they take turns? What do they do?
They transmit one item at a time from one PC at a time.
Okay.
They don't do it at the same time.
Protocol is called CDMA.
CDMA. I don't remember that one.
Yep. All right. Well, we'll get into it. Let's go back to our presentation and go through that. Let me see. Where am I? Here. All right, so we said that link access, we use MAC addresses used in the frame headers to identify the source and destination. MAC addresses are different than IP addresses, okay?
Right.
The other thing that we are interested in is reliable delivery between adjacent nodes, okay? So when two nodes are communicating with one another, how do we ensure reliable delivery? Well, that was something that we covered in Chapter 3. But we can also use something called parity, all right, to determine potential problems in our transmission. Now, for connections that have a low bit error rate, okay, very few errors, such as fiber and some twisted pair, we don't often use this capability. However, with wireless links, because there is a high error rate, we would use these techniques, okay, to ensure reliability. So why both link level and end-to-end reliability? Remember, where is end-to-end reliability performed?
Link layer.
No, not in the link layer.
Like in the link?
End-to-end reliability is performed at the transport layer.
Transport.
So why the end-to-end reliability and link level? Are all transport layer communications, okay, do they all provide the same level of error checking and so on?
Not everybody, no.
Yeah, because if you recall, okay, tell me the two types of segments that come out of the transport layer.
TCP and UDP.
Right. And TCP is connection oriented and UDP is not. So UDP could take advantage of the link level error checking, okay? All right, moving on. The other thing that we have to work on in the link layer is flow control. In other words, pacing between the adjacent sending and receiving nodes. All right, so the receiving node must be able to tell the transmitting node, hey, slow down, you're sending too much too fast, okay?
Right.
Error detection. Errors caused by signal attenuation or noise, okay? So what this does is it messes up the data. The receiver detects presence of errors and signals the sender for retransmission or drops the frame, okay?
Right, so for example, the error detection correction is where it checks the spread errors through the signal attenuation, electromagnetic noise.
Right.
And then it does, and then it catches, then it causes, then it for the transmitting node includes error bit detection and in the frame, and then the receiving node performs an error check.
Yes. All right, good. Okay, so next, error correction. The receiver identifies and corrects the bits or errors without even resorting to retransmission. How do we do that? How are we able to correct problems?
So, like, for example, for error correction, the receiver determines what errors occur in what the receiver knows determines in the frame when the error occurs and correct it.
Okay. Well, it uses parity, remember? It uses parity.
Parity?
Yes. Remember? And this is also where the CRC comes into play.
I remember that parity part.
Well, we're going to go into parity more, but I'm just giving you the term, okay, for right now.
Okay.
All right. One moment. Okay. So, whenever we talk about link layer services as well, we have to talk about different types of transmission modes. Half duplex and full duplex. Half duplex says that both sides may transmit. However, they must take turns. They cannot do it at the same time. Okay?
Right.
Full duplex means that both ends can transmit at the same time. What devices, let me ask a question, what devices provide only half duplex? Only one device at a time may transmit.
It'll be like switches?
No. What other device basically transmits in half duplex?
Like routers?
No.
So what device?
Okay. Hubs are half duplex. Switches are full duplex. Does that make sense?
How are they full duplex? That one, this part doesn't make sense.
I'm sorry, say that again, Sam.
That one doesn't make sense.
Okay. If you recall, with a hub, what happens when two devices attempt to transmit at the same time with a hub?
It collides.
It collides, which means that on a hub, they have to take a turn. They can't both talk at the same time, right?
Right.
Well, that's half duplex. But on a switch, are two devices allowed to transmit at the same time?
Yes.
Yes. So switches are full duplex. Remember, half duplex says that only one host can transmit at a time. Full duplex says that, both the sender and the receiver can transmit simultaneously.
Okay.
Okay.
Could you write down whether it's half for hub, whether it's half duplex? Could you write that down?
Okay, 1 second. All right. Now, let's move on here. All right, so where is the link layer implemented? As we can see, the half of the link layer is implemented on the network interface, okay, network interface card. And the other half is actually implemented within the processing of the CPU.
Yes.
Okay. So in each and every host, the link layer is implemented in an adapter, namely the NIC. Okay, and this would be, let's say, a Ethernet card, PCM CIA card, or an 802.11 card. An 802.11 card is a wireless card. And it implements the link in the physical layer. This attaches to, the card attaches to the host's system bus, and a combination of hardware and software and firmware then perform the upper layer portions. That's why the data link layer consists of two parts. Okay?
Right.
All right. So, as we look at the adapters communicating with one another, remember an adapter is a physical device. The sending side encapsulates the datagram into the frame, adds the error check bits, okay, the RDT, the flow control, and so on. And it sends that over in the form of a frame, which is then transmitted via bits over to the receiving side. The receiving side looks for any errors, examines the RDT, and also examines flow control. And it extracts the datagram, namely the frame, and passes it to the upper layer at the receiving side. Okay?
Right. So it extracts the datagram.
Right. Okay. So, five two, error detection and correction. Now, he said you just didn't have to know how to calculate error, the bit rate, correct?
Right. We didn't have to, for that one, hold on. For that one, For 5.2, know what parity bit checksum and CDO are used for, what the limitations are, but you're not going to be asked to calculate any of them.
Okay, very good. So, first we have error detection. So, in each frame, we are going to have what are called error detection and correction bits. These correction bits are redundancy, and they allow us to actually correct after an error occurs. D is equal to the data that we are attempting to transmit, which is protected by the error checking and may include header fields. Error detection is not 100% reliable. Protocol may miss some errors, but it doesn't happen often. The larger EDC fields yield better detection and correction. So the bigger the EDC is, the more data that we use, the better our error recovery capabilities are. Okay?
Okay.
Now, single bit parity. When we talk about single bit parity, what happens is you look at the data bits and then you calculate the parity bit. Parity is often described as even or odd. Depending upon the number, you count out the number of 1 bits, and if you have odd parity and an even number of bits lit up, then you set the parity bit to 1. Okay?
So if it's odd, you set up to 1?
Let's work through an example. Hold on. Okay. God bless you.
Thank you.
So we're going to be using odd parity. And you have to decide on whether you're using odd or even, or find out from the system what it uses. But it's typically one or the other, okay?
Yeah.
God bless you. It can't be both. So here we have 7 bits. Okay?
Right.
Now, how many bits are lit up? How many bits are on?
5.
5. That's an odd number of bits, correct?
Yes, but equal to 1.
Okay, so we're going to set our parity bit to 0.
0?
Because we want odd parity. We want an odd number of bits lit, okay? Let me do another example. Wait a second. Okay. How many bits are lit?
4.
There are 4.
So it would be 1. Even.
So we want to make the parity bit 1. This way it keeps odd parity.
Could you write that down? Would it be even? Can you write down?
Yeah, I'm not sure what to write down. Okay?
Yeah. Okay.
All right. Next, we have something called two-dimensional bit parity. Okay? Now, what's nice about two-dimensional, number one, it allows us to not only detect that an error has occurred, but it also allows us to correct sometimes certain errors. Okay? Not all errors, but some errors. Okay?
What?
So that's all you have to remember. Two-dimensional bit parity will both detect and correct single bit errors, while single bit parity only detects single bit errors. Okay? You see the difference?
So this one, the two-dimensional detect and correct single beta.
Yes. All right. Internet checksum and the goal, detect errors in the transmitted packet used at the transport layer only. Okay, so this is used up in the transport layer, not necessarily the data link layer. So the sender will treat segment contents as a sequence of 16-bit integers. The checksum, the addition of one's complement sum of the segment contents, and the sender puts the checksum value into the UDP checksum field. Okay, the receiver on the other side computes the same checksum of the received segment and check if the computed checksum equals the checksum that was saved in the field. Okay, if they are equal to one another, no errors are detected. Okay?
Right.
I'm sorry, if they're equal, no errors are detected. If they are not equal, no, then errors are detected. Okay?
Okay.
All right. So, checksumming, CRC or cyclic redundancy check. So, we're going to look at our data bits, which are designated as D, as a binary number. Choose an R+1 bit pattern, okay, which is our G. And the goal is to choose R CRC bits designated as R such that D comma R exactly divisible by G or modulo 2. Okay?
Right.
The receiver knows G and divides DR by G, and if it's a non-zero remainder, an error is detected. Again, you're not going to have to calculate this stuff. You just have to know what it is. All right?
Okay.
So, again, the CRC allows us to detect errors in the data, and it is often part of the frame. Okay? So, again, the CRC is widely used in Ethernet, 802.11, Wi-Fi, and ATM. All right. Okay, well, he's saying he doesn't want you to know how to calculate it. So we'll just leave this alone. And let's talk about multiple access protocols, okay?
Okay. Could we stop at 9?
All right, we can stop at 9, but let's see how we do with the multiple access protocols. Okay.
Oh, okay.
So anyway, when we talk about multiple access protocols, links and protocols, there are essentially two types of links, a point-to-point or a broadcast. PPP is often used for dial-up access. When we used to use the old modems, we used to use point-to-point links. Okay? Also, in a switch, that is a point-to-point connection between the switch and the host.
Okay.
Broadcast. Okay? Shared wire or medium. Okay? So, what device would you consider to be shared?
It is like LAN. You'll be.
No. What device? Think about the different networking devices that we have.
We have routers.
Right?
We have hubs.
Right?
And we also have switches.
Okay.
And we also have dial-up modem.
Okay. Now we said that an Ethernet switch has essentially point-to-point connections. So what device do you think has a broadcast type link?
Switches and hubs.
No, not switches. We said switch was like point-to-point. A hub is a broadcast. And that's why they say here under broadcast, old-fashioned Ethernet. Okay?
Right.
Also, upstream HFC, all right, as well as 802.11 wireless LANs.
Right.
Here are some examples of a broadcast environment. A bus configuration is a shared wire, shared RF in a wireless network, or shared RF in a satellite connection, or a shared acoustical air or space with people at a party. Okay?
Or a shared network, or like a shared mobile hotspot. Can share the network outside, or we can have Wi-Fi that shares to the public.
Right. Okay, so single shared broadcast channel, when we talk about multiple access protocols, two or more simultaneous transmissions by nodes interference. This is called a collision.
Okay.
In order to avoid collisions, we have what's called a multiple access protocol, a distributed algorithm that determines how nodes share a channel and determine when the node may transmit. Communication about the channel sharing must use the channel itself. No out-of-band channel for coordination. In other words, there's no other link for communicating the sharing of the channel. Ideal multiple access protocol, broadcast channel of, okay, here we get into the calculation. Let's break it right here, Sam.
Okay.
Okay? We'll get into this. When are we going to get together again? Tomorrow night?
Let me see about tomorrow night. Yeah. Let me text you because let me text you. Jim, let me text you when I'm available.
Okay. Well, I need a little heads up, so don't wait last minute, okay? But yeah, let me know when you can, okay?
I'll let you know if I can. I'll try to do this after work, but yeah, it's harder for me to do it during work. But let me give you a text and I'll give you a heads up. And
All right. Very good.
I'll try not to do at the last minute.
All right. And I just, we're running out of time. We're getting close to when we have to take the exam, so we need to take advantage of all the time that we can get our hands on, okay?
Okay.
All right. Very good, Sam. Well, listen, have a good night, and I'll wait for your text.
Okay.
Okay? Thank you.
You're welcome.
Bye.
Bye-bye.